So we'll talk about the entropy and Ricci flow convergence.
So first, I would like to thank the organizer for the kind invitation. I will talk on the entropy method and the Ricci flow convergence. However, in my mind, I will focus on the study of the killer Ricci flow on a closed manifold. So this is motivated by the study of the killer Ricci flow on closed manifold. So yesterday we have seen the excellent setup by Ben. So start from a closed killer manifold, you run the Ricci flow, then this Ricci flow has a very excellent property. The flow will exist if and only if the killer class is positive. If and only if omega t stay in the killer class. So yesterday Ben focused on the flow. Unnormalized flow. Right. Today I will put a normalization constant. So I have a lambda. Lambda is a constant. So it's clear up to a rescaling that there are only three possibilities. This lambda is a positive 1, minus 1, or 0. So what do we focus on is the killer Ricci flow. So of this equation, and it has a long time existence. We assume this flow. So starting from killer manifold, and it has a long time existence. And we also assume this flow is almost normal killer Ricci flow. So we call that in the literature, normal Ricci flow means the volume is preserved. The volume is a constant along the flow. Now we kind of let this volume is almost constant. In other words, it's bounded from below and bounded from above. So we assume this omega t to the power n. Bounded from above and bounded from below. Kind of, this is a condition. We call this condition as a quasi-normal. This is a uniform constant that depends on the flow. Now, we are interested in the time infinity behavior of such flows. So first, let's see, what can this flow be? They are very restricted, as explained. It's a similar discussion as done by Ben yesterday. So one can calculate the evolution of the killer class. So let omega t be the killer class. So you evolve the killer class. And you see this will be the negative of the Ricci plus lambda over omega t. And then this negative Ricci becomes negative over C1 of the manifolds plus lambda omega t. So then we consider the simple calculation. We consider the first case, this lambda is 0. Of course, this will be reduced to the case discussed by Ben yesterday. So lambda equals 0, so this is unnormalized. But we put a condition here. You can see that this omega t in this case is if lambda equals 0, so it will be omega 0 minus C1 m times t. And we assume the flow to exist forever. So it exists from 0 to infinity. And you know, for each t, for each t, this is greater or equal to 0. So that means this C1 of m will be less or equal to omega 0 over t. And now you let this t tends to infinity, what you obtain is that C1 m will be less or equal to 0. All right. And then we have this second condition. It's quasi-normal. So you can calculate the volume of the manifold. So the volume is it says the volume of to do this expansion, so it is omega 0 to the power n, very, very elementary stuff. And then plus negative C1 m to the power n, t to the power n. But we know this is uniformly bounded. We assume this is a condition. So for each t, this is bounded. So that means this is a polynomial which is a bounded number. That means it must be a constant polynomial. So all the coefficients must be 0. So in particular, you will obtain that. So like that C1 m dot omega is 0, and then C1 to the power of C1 m dot omega to the power n minus 1. This is also 0. Okay, so then you force that the C1 m must be 0. We already know that the C1 is less or equal to 0, and this quantity forces that C1 must be 0. So that means if lambda equals 0, you have a long time existing quasi-normal Ricci flow, then it must be the case C1 equals 0. Then the flow converges and no singularity happens. There is no singularity. So this is by the fundamental work of Professor Tao. So the interesting thing is the case. We are more focused on the case when lambda is non-zero. So we consider the case when lambda is not 0. So as we say that this lambda should be positive 1 or negative 1. And then by solving this ODE, this is quite elementary. Let's say this ddt of e to the negative lambda t over this will be negative C1m times e to the negative t. Okay, so then I will just copy down the result. You know, the first case is lambda equals 1. Second case, lambda equals negative 1. Now we see what is this omega t. I just copy down the calculation result. This is elementary ODE calculation. So in the first case, lambda equals 1. We can calculate that this omega t is C1 plus omega 0 minus C1m e to the power t. So this means omega t according to our assumption is a smooth solution. So this is greater or equal to 0 for every t. Right, so that means this one must be 0. Because we have two conditions. One is omega t is greater or equal to 0. The other condition is this quasi-normal condition. This volume is bounded. If this number, if this is not 0, then this will dominate the volume. It's impossible. So this means M is final. So this is the calories flow on the final manifold. So if lambda equals -1, then the calculation shows that this omega t will be negative C1m plus omega 0 plus C1m e to the negative t. Of course, you also know this omega t is greater or equal to 0. But then you have this quasi-normal condition. Now, there is a difference, because here, this power is e to the negative t. You cannot say, when t tends to infinity, this cannot dominate, because this vanishes, converges to 0 exponentially fast. So, what you can obtain? What you obtain in this case is actually C1m less or equal to 0. And you know, when t goes to infinity, this part almost does not contribute to the volume when you take omega t to the power n. So the volume is dominated by the first part. So you know this is C1m to the power n. Let's say this one. This is non-zero. Okay, so now in this, we know that you still have two cases. The first case is C1m is strictly positive. Then again, this return to the theorem of Professor Cao. So you have a convergence, no singularity. So the interesting case will be the case when C1m is only less or equal to 0, but not strictly 0. And C1m to the power n is non-zero. So this is the case. In this case, as introduced by Ben yesterday, so in this case, we know that the manifold is a minimal general type. So now we can compare these two calorie flows. So we know you have two cases which is completely understood. So the interesting case for us now is the case when the manifold is final, and the case when the manifold is minimal and general type, but not strictly C1 less than 0. So now I compare these two flows. I found that there are many similar properties between these two flows. So let's say this category A is the final case, and the category B is a minimal general type calories flow. So we copy down the equation. The first equation will be the flow equation ddt of g equals negative Ricci plus g. The second equation in this case, it is ddt of g equals negative Ricci minus g. Okay, so this is the equation of the metric tensor. You can also see the similarity between these two flows by considering the evolution equation in the potential level. So the equation of the potential is ddt of u equals log omega t to the power n over omega 0. This u is the Ricci potential. Sorry, u dot is the Ricci potential, so u should be the potential function. Just in this case, the flow run in the same class. It's only determined by a potential function. This can be added by a constant. So I do not put the normalization condition here. And similarly, for the potential level of the general type Ricci flow, you have this ddt of u equals log omega t to the power n over capital omega minus u. So this is a minus sign. So what is this u? What does this u mean? So actually, in this case, what do we have? We have this omega t. Because the class is evolving. So it is this. We have omega t equals to chi plus e to the negative omega 0 minus chi plus square root negative 1 partial bar of u. So this is the class. This represents the class of the metric. How do you choose this chi? So and how do you choose this capital omega? So capital omega is a volume form, and the chi equals greater or equal to 0. So you know this corresponds to the case C1 less or equal to 0. So here you have this chi greater or equal to 0. This is solving Morantini equation by Gauss fundamental theorem. Okay, so now let's list another basic property by comparing these two flows. I consider the volume, the global volume along the flow. So you know the volume is nothing but the integral of omega t to the power n. But in the final case, this omega t is always C1. So this is nothing but C1. So this is a constant. It is really a normalized Ricci flow. So the volume is a constant. And then you compare this minimal general type Ricci flow. This volume I should not write this. Then it's determined by the class here. So it's also not very hard to calculate. The dominant part is a chi to the power and then plus but when t goes to infinity, these are small terms. It can be it's not important. So this means the volume will converge as t tends to infinity. The volume converges to the chi to the power n, which is negative C1m to the power n. So this is not 0. So this is I think this is the reason why this is called the non-collapsed case. Right. So you compare these two Keller-Ricci flows. So the volume behavior is similar. Under the final manifold, the volume is a constant. Under this minimal general type Keller-Ricci flow, the volume is almost a constant when time is large. So we expect that they behave similarly. Okay. So now we first go through the estimates we can obtain for the type A, the final Keller-Ricci flow, and then by comparing these two Keller-Ricci flows, we try to obtain the information to study the kind B, the general type Keller-Ricci flow. So now we return to this name. We say that the entropy method and the Ricci flow. So because when we study the type A, the final Keller-Ricci flow, the entropy play a fundamental role. So now we want to use this entropy to get some information to study the general type Keller-Ricci flow. So then I will talk the similar subject as been discussed yesterday, but from a different perspective. I expect that we can obtain some supplementary information. So now we focus on the flow A. Now we see how do we understand the behavior of the flow A. So first let's list some known estimates along the flow A. So using the entropy of Perman, he shows that the scalar curvature and the diameter of the flow is bounded. The scalar curvature as diameter, this is uniformly bounded along the flow. So this is a fundamental step to study the behavior of the Keller-Ricci flow. Note that scalar curvature is bounded. Again, using the entropy, Perman shows that this flow satisfies the kappa non-collapsing property. So that means the volume of Bxr over r to the power 2n. So recall n is a complex dimension, so 2n is a real dimension. It's greater or equal to kappa. So every x is a manifold, r log to large. And this is for every t. So t does not appear explicitly, but it's taken from some t time slice. Okay. So this is kappa non-collapsing. So it's this kappa non-collapsing is the essential difficulty, even in the proof of in Hamilton's program of the proof of Poincare conjecture. This is a key difficulty. Then I list another estimate. So using the entropy method, one can obtain the heat kernel on diagonal up bound. So this is by the work of Qi Zhang. Then apply this heat kernel up bound. One can show that actually this volume ratio has an upper bound. So this means say this. So this is greater or equal to kappa inverse. I choose the kappa to be a small positive number to be simple. So this is so the first result is by Theorem, 2003. And the proof was refined and written very explicitly by System and Tian. So these are the fundamental estimates of Keller-Ricci flow on final manifold. Okay, so then one want to study the convergence. But here it's a little bit tricky. So what does the convergence mean? You have to delicately choose the convergence topology, right? So if you choose a very weak topology, you already obtain the convergence. So the volume is fixed, and then you have this volume doubling property. So in the Gromov-Hausdorff topology, you already know every time sequence have a convergent subsequence, converging to some limit metric space or length space. So that's easy. When you have this volume doubling, you know that you converge to a limit space. But the point is we want to more refine the convergence. But then this more refined convergence or more refined topology, you still have a lot of choice. You can consider this flow. You can consider the flow in the potential level, right? To see if you converge to a smooth limit U infinity. This is also a convergence. But this is too strong. It's almost impossible. You have example. Actually, you consider the CP2 blow up 1 point. At that example, this U does not have a limit. So if you converge to Keller instant. But you start from CP2 blow up 1 point. There is no Keller instant. So you does not converge. So the question for the convergence is to choose a proper topology. And it turns out this is, we call this C-hat infinity Chigger Gromov topology. Which means, this definition is a little bit complicated. I will not explain that in detail. So that suppose you do not have this C-hat infinity. In general, Chigger-Gromov topology means the convergence in smooth topology up to a diffeomorphism. Modular diffeomorphism, you have smooth convergence as tensors. You need to consider the behavior of the diffeomorphism. But now, put this means you have a limited space which is almost a smooth manifold, so smooth away from codimension four singularity. Then the convergence is in Gromov-Hausdorff topology globally, and when you restrict your attention on the smooth part, the convergence is smooth in smooth Chigger-Gromov topology. Well, so I will not explain in more details of this. It's just some refined topology. It's more refined than Gromov-Hausdorff topology, but it's weaker than smooth Chigger-Gromov topology. Okay. Right, so for this, what do we do? So the progress, I list some important progress. So in dimension 2, so we proved this in 2009. In dimension 3, so this was done by Tian Zhang. 2013, and in general dimension, this was done in 2014. Right. Now I explain some of the key steps to show this convergence. So these three use different methods. So here we use the orbifold companions. For dimension 2, we use the Canonical flat orbifold companions and then obtain some regularity argument. Here, Tianzhang's argument uses the LP norm bound of a Riemannian curvature, P greater than a half dimension. So choose P equals 4. That's y. Yn equals 3. And the method we do for the general dimension is based on the following observation. So we observe that this three-heading Ricci-Gromov topology happens in the study of Cheeger coding theory. So suppose now I consider only the simple case, let's say Ricci greater or equal to 0 and a non-collapsing. Suppose you have a sequence of manifolds with Ricci greater or equal to 0, then it converges to a limit space. If you know even further that it is Ricci flat, then the limit space has much better regularity because this is elliptic PDE. You can improve regularity from the elliptic PDE. So in that case, you know that the limit space will have a regular singular decomposition, and the regular part is a smooth manifold. And then you consider Hamilton's Ricci flow. What you obtain is the Ricci curvature equals. Now I rewrite the Ricci flow equation as Ricci equals to the negative modular constant. So kind of in Cheeger coding theory, you study the elliptic version. Now Hamilton's Ricci flow, you have a parabolic version. So you should have a parabolic version of Cheeger coding theory. That's just an intuition. That's not an argument. But how do you make this intuition become an argument? So we essentially use the property that the scalar curvature is bounded. This is the essential property you can obtain by Perelman's estimate. So we find that to study this is more complicated. We study first the simplest case. Consider the case that the scalar curvature equals 0. Here. You suppose you have a Ricci flow and scalar curvature equals 0. Then you have this equation, ddt of the scalar curvature. This will be twice Ricci square modular constant. So so if it's 0, then this is 0, then this is 0. So you will obtain this is 0. So that means in the infinitesimal level, actually the local structure of the Ricci flow with bounded scalar curvature must be the same as the Ricci flat space. Because scalar equals 0 implies Ricci equals 0. Actually, we have a more precise description of this. There is an inequality that Ricci curvature can be dominated by square root of Riemannian curvature times scalar curvature, like that. So when scalar curvature equals 0, you obtain Ricci curvature equals 0. So that means you need to first to study the Ricci flat space very carefully. But this Ricci flat space should have mild singularities. So we should consider, so this means model space are Ricci flat space, but with singularities. Why is it with singularity? Because even you consider the Chig-Cooling theory, you have a sequence of Ricci flat manifolds. You take a limit, you still obtain a Ricci flat limit with mild singularity, right? Here we have scalar bound, so this works. And we have one more condition. We have the manifold is scalar. Okay, so then you can use the Chig-Cooling theory to obtain the singularity actually are very mild. So actually the singularity codimension greater or equal to 4. This is a key point. If you have a codimension strictly greater than 2, then the companions theory of Chig-Cooling for remaining manifold and for the singular space with codimension greater than 2 are almost the same. Where you have this regular part convex. Okay, so that's the basic motivation for this. Another thing is here it's a motivation from the equation. From the equation, but there is a key thing, which is the convexity of regular parts. So when you deal with the space of the singularities, you need the singularities to be mild, which means codimension greater than or equal to 4. And also you need the regular part to have some property. So the regular part converges to regular part, singular part converges to singular part. So the interaction between the singular part and the regular part is very small. So how do you obtain this geodesic equation? So we use a key observation here is to use reduced geodesic, which we will use later. So we have two tools from Perman. One is the entropy, and one is the reduced geodesic. Okay. So maybe I review something of the reduced geodesic. For a Ricci flat manifold, the reduced geodesic becomes geodesic. So now we consider a Ricci flow solution. So this is a Ricci flow space-time. We regard the Ricci flow as a space-time. So the horizontal part is the manifold direction. The vertical is the time direction. Now, for simplicity, now let's consider this as t equals 0, this as t equals 1. Then I define a new parameter tau equals 1 minus t. This is not me defined, so it's defined by Perman. So I choose a point x0, 1 here. This is a base point in the space-time. Then I choose another point at the time t equals 0. I choose the point y0. Okay, so we consider a space-time curve, which I denote by gamma. So gamma parameterized by tau. So now I say this, how do I say? This bigger gamma. This is a bigger. So it has a gamma tau, 1 minus tau. So this is a space direction. So this is time direction. So actually you connect the 2 points in the space-time by a space-time curve. Then there is a Lagrangian of this gamma. So this is the integral from 0 to 1 of the square root of tau over r plus gamma dot square d tau. So this is the Lagrangian, right? Then you have another curve. You consider if there exists a minimal, if there exists a curve to minimize this Lagrangian. Okay. So the minimizing space-time curve exists. And it is called a reduced geodesic. So this is Perelman's invention for the Ricci flow. Now, the interesting thing is when you have a Ricci flat manifold, you can regard this Ricci flat manifold as a trivial Ricci flow solution, right? So this reduced geodesic has 2 explanations. One is you regard this as a Ricci flow solution, and the other is from the Riemannian geometry point of view. So now, if we consider, suppose the Ricci flow space-time is trivial, or in other words, is Ricci flat. Then what is the Lagrangian? It is the square root of tau. Now the scalar part becomes 0, right? So it's just, and this gamma dot originally should be GT, but this GT now is equivalent to G, does not evolve. So somehow you are up to some rescaling. This you are normalizing. So you are minimizing this Lagrangian gamma dot square d tau. This is nothing but the energy in Riemannian geometry, right? So a curve minimizing energy is nothing but the geodesic. So geodesic and the reduced geodesic coincides in this case. Okay, so that means you in the local behavior of the Ricci flow, the Keller Ricci flow with bounded scalar curvature, should be understood by the behavior of the reduced geodesic. Okay, so this is one of the key points. So then let's go back to the basic setup. So to study the convergence of the final Keller Ricci flow, we know that we need to bridge 2 group of information. One is the Chick-Coding theory, and another is Hamilton's Ricci flow. And we also need Perelman's reduced geodesic. So what do we do? We generalize Chig-Cooling theory from manifold singular Canonical flat manifold. So we want to bridge these two theories, but you cannot bridge them directly because they are not developed for this bridge. So you have to modify one of the theory a little bit. That is the Chig-Cooling theory. We generalize this Chig-Cooling theory to singular Canonical flat manifold with codimension 4. We define a model space. This model space is really flat space with singularities non-collapsing. And kind of this model space is compact on the C hat infinity Chig-Gromov topology. Okay. This compact means you can obtain some estimates. Then using these estimates, we can define a radius. So a radius which quantizes this observation. So we know that in the infinitesimal level, the flow spacetime can be modeled by the Ricci flat spacetime. But then we want to see precisely on which scale you can obtain a similar estimates of the model space. For this purpose, we define a quantity which is called the canonical radius.
What do you mean by singular Taylor Ricci flow? Singular means singular in the initial data or what?
But the underlying space has singularity, not smooth. It's not a. Okay, like a orbifold. A simple example for this is like orbifold. You have a cone singularity here. Away from that, you have smoothness. We consider the Ricci flat space with some singularities, but singularity are very very mild. Yeah, so that's
Point singularity.
it's not a point. You could dimension 4 singularity. This is just a very simple example. It's definitely it's satisfies the condition. Okay, so then also basically after we observe this, the proof of the convergence theorem is this. So we define canonical radius. Then show the canonical radius uniformly by bounded from below by a constant, by maximum principle. Basically, if it's not bounded from below, you can rescale at some critical level. Then you obtain on one hand side you converge to the model space. On the other hand, its canonical radius is bounded is 1. But according to its definition, the canonical radius is infinity for model space. Okay, so this is a very interesting definition. So you can regard this as a generalization of the harmonic radius. If you regard the model space as Euclidean space, then canonical radius is the harmonic radius. So this is a generalization of the harmonic radius. Okay, so I have briefly discussed the idea of the proof of the convergence for the final Canonical flow. All right.
On the other hand, for the dimension for the curvature is essentially bounded, right, or something outside that for the dimension.
Yeah. So away from the singularity, in each compact set in the smooth part, the curvature is union-bounded.
In the 3 dimensions, there's the LP estimate, right?
Right. They have a LP estimate because P greater than half dimension. There is a comparison geometry. You definitely need the comparison geometry picture, but here we use the comparison geometry picture of the reduced geodesic and reduced volume. Okay. And we show that because you know that.
So that you get the using these to try to get the curvature.
Yeah. You do have some a priori estimate, which is a comparison geometry style. So we use space time. So the observation is you regard the Ricci flow as a space time. So then the interesting thing is the convergence of the space time. But this space time is the space because after blow up it is the trivial space time. So you can regard the Ricci flat space either as a Ricci flow or as a remaining geometry as a manifold. That's the basic thing. These two can be glued together in this setting. Also, I basically described the basic idea how to use it. So then, so in the next lecture, I will apply such idea or similar observation to study the Keller-Ricci flow on the general type manifold, which is minimal. So I think I'll stop here. Case stability?
Yeah.
Oh, so that's even one more step. So after you have this convergence, you know the limit is a soliton, Keller-Ricci flow soliton. Keller-Ricci soliton. So then there is a generalized stability with respect to Keller-Ricci soliton.
Okay.
Yeah, so by Nystrom and his co-author. So we show that this convergence, if the flow converges to a Keller-Ricci soliton, what should I say? So
You can have calculation or not. Use this definition.
So the thing is this. So you want the limit the same as the original manifold, right? If the limit is different, you can construct a test configuration.
Basically, I guess in general is you would have to have some test configuration, and if it's stable, then that actually and then you have to keep the same. At least like commission Young medicine, those things will.
Yes.
You produce some structures, right, and then try to
Right.
balance stability.
Mm-hmm.
And
Yes, this is a basic argument. But there is a key difficulty which for this argument. So originally we thought that you can construct a test configuration. So you suppose you start from M, then you have MGT, I converge to some M hat, G infinity. Now you put some, you obtain some test configuration. So you have a central fiber. We say this central fiber is M hat, and the general fiber is M. But this is not the case. This is a very natural case, but we stuck here for a long time, at least for 2 years. The reason is this Keller-Ricci soliton equation I j bar plus j bar minus j equals 0. This gradient f, this as a holomorphic vector field, it may be not rational. So it does not. So in general, it's impossible to obtain such a degeneration. So what do we do is to construct 2 steps of degenerations. So this is a combination of the 2 steps of degenerations. But basically, so you consider m degenerate to some m tilde, then you m tilde to consider degenerate to m hat. So one of them will be the contradiction degeneration. So there you can construct 2 test configurations. One of the, if m hat is different from m, among these 2 degenerations, there is 1 which gives you the contradiction. In the case when m hat is Kähler-Einstein, singular Kähler-Einstein, this m hat tilde and m hat are the same. There is only 1 degeneration.
So now let's send the one again. So we have a full photo in the first row, like very quickly. So it's